Eso lo digo.
But anyway, the opportunity was worth it.
Okay. Isabel, mira,
Venga, vale. Sí, eso. Venga.
Okay, what time is it? I think it's already the time.
Well, people are still coming.
Minutes, I think. We had Stephen Hawking was here something like 20 years ago, something like that, and it was something similar to you. I mean, it was not still ready, this auditorium. There was another one, but there were also something like 400 people like were here today. It is quite amazing.
It's a nice auditorium.
Yeah, it's a very nice auditorium. It's a pity that the quality of is not so good of the image, but they are trying to improve it. But it takes a while. Let's see. I think we should start. To us right now. They are checking whether there are people on the queue for translation. If there is nobody there, we will start. Okay?
I'm easy.
First, to be sure that nobody is still there.
No,
right
people
now,
are.
let's go just to check that. As soon as we get the okay, we'll start. Hola. Buenas tardes y bienvenidos todos al Parque de las Ciencias de Granada, a esta conferencia conjunta organizada por el Instituto de Astrofísica de Andalucía, del Consejo Superior de Investigaciones Científicas, Centro Severo de Excelencia del Ministerio de Ciencia y Innovación y el Parque de las Ciencias de Granada. Voy a hacer la presentación en inglés ya que se dispone de traducción simultánea, ¿vale? Today we have the privilege to have a speaker, the Nobel Prize in Physics 2020, Professor Reinhard Genzel. Professor Genzel received a diploma in physics from the University of Bonn in 1975 and the doctorate in physics and astronomy from the Max Planck Institute for Astronomy in Bonn in the year 1978. From 1978 to 1980, he was a postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics in Boston. In 1981, he became an associate professor of physics at the University of California, Berkeley, and he became a full professor there in the year 1985. Since 1986, he is director and scientific member of the Max Planck Institute for Extraterrestrial Physics in Parque, Germany. Professor Genzel has received many prizes and awards, including the Gottfried Wilhelm Leibniz Prize of the German Research Foundation in 1990, the Balzan Prize in 2003 for his work on infrared technology, the Shaw Prize in 2008, and the Crawford Prize in 2012. But as mentioned before, Reinhard Genzel, director of the National Institute in Parque, received the Nobel Prize for Physics in the year 2020, together with Roger Penrose and Andrea Guest. Professor Genzel's work spans both galactic and extragalactic astrophysics. He and his group made pioneering observations to map the motion of stars close to the galactic center, leading to the firm evidence for the existence of a supermassive black hole at the center of the Milky Way into an accurate estimate of its mass. Using high-precision methods, Genzel's group also observed bursts of brightness from gas in the immediate vicinity of the black hole and a gravitational redshift caused by this mass monster in the light of the passing star. Today he will detail some of these results in his lecture entitled Galaxies and Black Holes, a 14-year journey. Thank you, Reinhard, for your availability to participate in this event. We are very pleased to have you here, and we are sure that you will enjoy your talk. The floor is yours.
Well, like you, the little one up there, it's great that you've come, all of you, young and old, and I invite you to a trip, to a journey through distant galaxies and to black holes. I'll explain to you, of course, as best as I can, what these things are and why we are so interested in them. Now, this journey is not something you undertake in an afternoon. It takes a little while because it is really experimental physics. We had to build equipment, build it better, still better, still better, all over a period of 40 years. But it was an exciting journey, and I'm trying to tell you why that was so. So, the story, and I think here it probably would be good to dim the light a little bit so we can see the screen. Can we? Wonderful. You don't need to see me so well. You need to see the screen. So this story deals with telescopes, of course, because that's how we astronomers do our journey. But initially, let's take a trip from where we are in our Milky Way, in our home galaxy, to the nearby universe. Let's take the lights out, please. And audio. Sehr gut. So these fuzzy things you've seen in this simulation are galaxies. There are billions of galaxies in the universe, and our Milky Way is one of these billions of galaxies. And our Milky Way consists of billions of stars. Just imagine the numbers. And it's about 100,000 light years across. So it takes light to pass 100,000 years to go from one side to the other. So these are the enormous structures of the universe, and this was just what we would call the local neighborhood. This is where you kick the ball around if you work at the speed of light. So this is our universe, which consists out of these galaxies, and the galaxies are largely made out of stars. Stars like our sun, but also more massive galaxies. Then there's a sprinkling of other stuff in the centers of those galaxies, interstellar material. That's, so to speak, the food out of which new stars are made in these galaxies. Stars are forming. Our own galaxy forms nowadays about one sun per year. That's not much. Actually, 10 billion years ago, it was about 100 times that much. Because then the universe was older, it was also more younger, and then it was also more compact. And so there was more gas streaming into centers of these galaxies. They grew fast, and they had something in their centers, and these are black holes. That we now know. Every one of those galaxies which you saw in that movie has a big black hole in their centers, between millions to billions times the mass of the sun. Now, that's remarkable. And I'll tell you that story. First, of course, I will explain to you what these black holes are. Then I'll tell you how we find them, how we can prove that they really do exist. And then I come back and will tell you what their role is in the universe. Now, this all started 107 years ago with Albert Einstein. Albert Einstein, in 1915, gave a speech to the Prussian Academy in Berlin to present to the colleagues a new theory he had come up with, which he called the general theory of relativity. He had 10 years before already produced a major piece of work, which is the so-called special theory of relativity. But this one here went one step further. It unified the fact that the speed of light is the largest, the fastest speed of communication in our universe, with the fact that light also sees gravity. We all know what gravity is. I can't do that because I have a bad knee, but if you jump up from your chair, you will know that you come down pretty fast. That's gravity. That's gravity, and we cannot, as human beings, of course, jump fast enough to leave the Earth. But light can. So if we send a light beam from here on out, it easily escapes the gravitational field of our sun, our Earth, our sun, and of course also the Milky Way. So this is what Einstein and his colleagues did. They tried to formulate in what we call a theoretical concept how this universe should be described if light also sees gravity. And that's, as you will see in a second, where these things we call black holes emerged. Now, he was not alone. There were others like him. Karl Schwarzschild, a year after Einstein's talk in Berlin, found the first solution, and that already had in them the first concept of such a black hole. Then 50 years later, Roger Penrose, with whom I shared the Nobel Prize, and Roy Kerr worked further on the problem, showed that actually these black holes are not just constructs of the theory, but likely would occur in the universe under certain conditions. Now, the theory of general relativity of Einstein is what we would call a classical theory. It holds on large scales. But at the same time, one of the predictions, as you will see, of the theory is that there are, at the centers of black holes, locations of infinite density, singularities. And that's something which is, of course, on small scales, and so that's where we believe Einstein's theory needs to be changed, needs to be added to. Physics, natural sciences, is a fluid kind of a thing. You don't know on Monday what the world is made out of. You make a proposal on Tuesday, on Wednesday, your colleagues will test it. And if it comes out all right, then on Friday you go on and check out whether the theory is also true in other circumstances. That's an arduous kind of a path, but that's how we can actually know something about the world, which everyone will have to accept in the end. And general relativity so far has passed all the tests, and we'll see today also the tests in the center of our Milky Way. So that's how it all started, with theory. Now, in that theory, the concept of gravity and how masses interact with each other is through the deformation of space-time. In Newton's theory, as you may recall, there was the idea that if you have a sun and you have planets surrounding the sun on orbits, well, then that force due to gravity would hold the solar system together. Einstein's way of saying this is if you have a heavy mass like this yellow-green object there on the right, that makes a dent in the space-time, and this dent is communicated through essentially speed of light, gravitons, to another object, which would be the smallish red thing, which might be a planet orbiting the sun. So it's the communication to the other one, which is not instantaneous. It happens through a communication which is at the speed of light. So says the theory. Now, in Newton's theory, if you have the sun and the earth, and there's a star behind the sun, such that a ray of light can just pass glancingly at the surface of the sun, then the expectation is that that ray of light goes in a straight line. That's been the assumption of all of Newton and many people since him until general relativity. In general relativity, the new thing is, as I said, also light sees gravity. So what really happens is the beam of light goes straight line initially and then is bent by the force of gravity onto the light. Now, if you think about that, if you're now on Earth and looking back towards the star, where is the star in your picture? Well, it's actually in a position, just a second, it's in a position where the star really is not, namely up there. Because you, in your mind, think the light goes along a straight line. And so you project, you project the image of the star to a distance of 1.7 arc seconds. That's a very small amount, but it's something you can actually measure. And indeed, in 1919, there was a solar eclipse in the South Atlantic, and 2 British expeditions used that eclipse to see exactly what I've shown you, the eclipse of stars whose positions were very well known by the sun. And sure enough, when the stars were behind the sun or at a glancing angle, they could see this effect of 1.7 arc seconds. That made Einstein a rock star in an instantaneous period, basically, because people couldn't just imagine how you could, with your mind, predict something which has such an enormous impact. So that's general relativity, and let's talk about black holes. So if you think of the sun, there it is, and in your mind you put a rocket on the surface of the sun and accelerate it to about 600 kilometers per second. Then that rocket can escape the surface of the sun, in fact can escape the sun and go into interstellar space. On Earth, such a rocket would have a speed of 11 kilometers per second. All of us modern humans in this room have seen such rockets on Earth. Our forebears wouldn't have known that either. But we know, in fact, you can get away from the Earth with a rocket. But now this speed, that is 600 kilometers per second, depends on 2 quantities. It depends on the mass of the sun and also the size of the sun. That makes up gravity. It's the ratio of mass over size. And so in your mind, you could think of another sun which has the same mass, but is smaller. Suppose we make it 3 kilometers in mass. Then we can calculate again what the rocket would have to move at in order to move away from the sun. And the number which comes up is 300,000 kilometers per second. Now, I don't know what 300,000 kilometers per second is. That's the speed of light. So that means that only a rocket which moves at the speed of light would be able to escape that sun. And if you make the sun, that sun, even this little smaller, well then not even light could escape. There you go, that's a black hole. And so that means your inevitable conclusion is that if there is such an object, there is a radius, which we call the event horizon, within which light cannot escape anymore. The mass is there, the gravity is there, but light cannot escape. So then you might ask, well, you can tell me all good stories, but how do I know that this thing is there? Well, we do the same as Newton and the solar system. We think that we can basically test this idea by looking at a system which has, say, planets around it. So this sun, with one solar mass, which is a black hole, cannot be seen, has the same planets, and the planets move in Keplerian velocity. That is, the nearby planets move faster than the distant planets. And we know exactly what the law is. It's 1 over the square root of the distance from the center. And so in that planetary system, same would happen. The only difference is the sun there does not shine. But we can see it through gravity. We can see it through the action of gravity onto the masses, in this case planets. So that's how we can actually see black holes. There's another way to see black holes, which is basically through the bending of light, as I explained. And then there's a third way of doing this, and that is through so-called gravitational waves. If you have two masses orbiting each other, then they lose energy and spiral inwards by radiating away the ripples of space-time, and that's called gravitational waves. And it's remarkable that 107 years after Einstein's astounding theory, we now actually have techniques from these three methods to show that black holes exist in three different ways. Now, it took a while, however, to have candidates. It's one thing to have a theory. The next thing is, where could we observe such a thing? And that happened in the 1960s in two ways. One was that the X-ray astronomers were able for the first time to look out in space, and they observed double stars. Normally, double stars, you see one star and another star orbiting each other. But in this case, you saw a star, and then something which wasn't there on the optical plate, but it was bright at X-rays. And after a while, the proposal was that the non-seen, the non-optically radiating object was what we now call a stellar black hole. Then the second discovery in the 1960s were the quasars. There, the radio astronomers had looked at the skies and found very bright radio sources which were highly variable. And they asked their optical colleagues, please look at the sky and tell us what you see. And then they took a picture, and what did they find? They found a little meek, stellar-like looking object where the radio source was. Not very impressive at all. But then Martin Schmidt there used a big 5-meter Palomar telescope in California to look at the optical spectrum. So you basically dispersed the waves in the optical and looked at that spectrum. And what did he see? He saw very sharp emission lines in the spectrum of this quasar. And the ratios of the wavelengths of these emission lines were exactly what was known from very well-known lines due to hydrogen, helium, and neon, etc. But they were all redshifted by 16%. So what causes that redshift, was the question. And at that time, already for some time, it was known that the universe is expanding. So that we look in the distant universe, then objects are moving away from us ever further. And the Doppler effect, due to the motion, then redshifts any emission. And so if you take the 16% and convert it into a distance, then it turns out that this meager little star is 2.4 billion light years away. That's a significant fraction of the age of the universe. At that time, it was a sensation. One only knew the sort of the immediate environment which we flew through in our movie. And because it's so distant, that means that this little meager star actually is extremely luminous. Because, of course, the further the distance, the weaker it appears, yet the emission at the locus of the star, of the object, is very large. In this case, it turns out that this quasar in the center of a galaxy has about 1,000 times the luminosity of our entire Milky Way. Now, mind you, the Milky Way has 100 billion stars, I told you. So what about this thing? Does it have 10 to the 3 stars more? Well, no, because actually the variation in time of the emission tells you that the emission volume, so to speak, is very small. It's only a few light years. So everyone thought, how can that be? So much radiation from such a small volume. And here comes the answer, which to you must sound completely paradoxical, given what I've said so far. Black holes. Wait, you say. You just told us that light cannot escape from black holes. Now you tell us that, light produces, black holes can produce some of the brightest objects in the universe. How does that fit together? The answer is that this event horizon is very small. For a 1,000,000 solar mass black hole, it's about as large as the sun. But if material falls into a black hole, in this particular case in a loopy, disky type configuration, then on the way into the black hole, the inspiraling gas turns gravitational energy or potential energy into radiation. And the remarkable thing is that before it disappears behind the event horizon here in the center, it can convert about 10 to 30% of the rest mass energy of a particle into radiation. The best energy source we have on Earth, although some of the countries don't want it anymore, that is nuclear energy, is 0.1%, so a factor of 1,000 less efficient than this. So the conversion of gravitational energy into radiation on the outskirts of a black hole is the most efficient way to produce radiation, theoretically. But is it true? You can tell me any kind of a story, my friend would say. You have to prove it. The scientific principle is you must prove it through measurement. How would you do this? Well, I told you how. By measuring the motions of these gas clouds slowly in spiraling, or not so slowly, and falling into the black hole. That's the way to do this. But this object is so far away that at least back then, in the 60s, nobody could think of making this measurement. We can do it now, but not then. But then, two very famous British theorists, Donald Lindell and Martin Rees, said, well, these quasars are very rare, very rare. They're also very distant. So maybe it could be that the reason they are so rare is that these quasars only occur if there's a lot of material falling into a central black hole. And maybe that very fact is rare. So most galaxies, maybe every galaxy, they said, may have a black hole, and only a few have so much accretion that indeed then you get that much energy. If that is the case, they said, well then you can look in more close objects, in galaxies which are much closer. And the closest one is our own. Our own galaxy is only 27,000 light years away from us, and that's 10,000, 20,000 times closer than any nearby active galactic nucleus like these quasars. So that's how in the early 70s, the idea was born to use the galactic center as the nearest galaxy to check out that proposal that there was a black hole in galaxy centers. Of course, in our own galactic center, not one which was very active. Okay, here we fly into the center of our Milky Way. We are living in a disk galaxy in the outskirts, in the outskirt villages and fly now into the center. All the stars you can see, and then you can see also this dark stuff. That's dust. That's interstellar dust, which attenuates the optical radiation. So actually, you cannot see the galactic center with your eyes or with optical telescopes. You have to go to longer wavelength, radio waves, and what we would call infrared waves. So wavelength which is a few times, 4 to 10 times the wavelength of optical light. And if you do that, then you see this region here on a scale of a few light years. In blue, you see very many stars. The stellar density in the galactic center is about 1 million times that in our neighborhood here. There is no night. If you were a planet in the galactic center, there would be no night. And then there is a very compact radio source in the center, and then there's filaments, streamers of ionized and neutral gas in this vicinity. Now the radio source, the radio astronomers checked out, is very, very compact in angular diameter. The size is astoundingly small, only about 50 micro arc seconds. That's about this much on the moon. And that thing is 27,000 light years away. So clearly, that's a remarkably compact radio source. So many people immediately suspected maybe if there is such a black hole, it might be right there. You just have to check it out. How do you check it out? Well, the first way of doing it is through this gas. Because if the gas clouds move because of gravity, well then they are pushed around and you can measure the so-called Doppler motions. Now in Berkeley, Nobel laureate Charles Townes had then moved to California after having had a terrific career on the East Coast. He invented the maser and the laser. But then in later years said, I've done enough of that. I now want to do astronomy. But he knew how to work in the infrared. And so he and his students, and I was then one of his postdocs and colleagues, went ahead and measured the motions of these gas clouds. And on this diagram, and I apologize for this more technical graph here, in units where every one of these ticks is a factor of 10, and the mass is going upwards, and the distance is going to the right. So Sagittarius star is here on the left, and then you go out. You see, at large distances, the mass changes with distance. And that's the hallmark of an extended mass distribution. It's just the stars, the extended stars in the galactic center. But inside of about 3 light years, the mass did not change anymore. And that tells you that there is a concentration of mass. So in Berkeley, we happily published a paper in Nature in 1985 saying there's a black hole in the galactic center, a few million solar mass black hole. Did we get the Nobel Prize? No. That's the fate of science. You have to convince others. And we did not, at that point, convince others because they said, well, gas is not a good way of measuring gravity. But more importantly, the distance at which we had made our measurements effectively is 1 million times greater than the event horizon of a 1 million solar mass black hole. They said, there could be all kinds of other stuff in there which you haven't seen. Weak stars, which are not very bright. Neutron stars had done, at that point, already been discovered. Stellar black holes, all objects which have mass, but, don't make much radiation. So, back to the drawing board. You have to do better. And that's when I moved to Germany, actually, to start a new group in Munich. And we started building new equipment, new technology, over many years to improve on the resolution, to use the stars as tracer of gravity instead of the gas, etc., etc. So that is the story. observatories in the world. Another one is Mauna Kea and the Keck telescopes, and that's the sites where we do our work. Now, of course, you may not know why I played the Bond movie from Quantum of Solace. Do you know? Well, actually, the last scenes play in the so-called residencia, where the scientists and the engineers sleep. And in the residencia in the movie, the Bolivian bad guy, has his headquarters. And then Bond and the Bond woman come and creep in there and then go over the roof, and they rappel down, and in the end, they kill the guy. Well, I was actually sleeping exactly where they would do their rappelling. Now, if you know anything about movie industry, they don't do this once, they do it 10 times. And I wanted to sleep. Okay, the EVLT for you, where we do our research. And at the same time, Andrea Guess, Mark Morris, Eric Beckley, and others in California started a similar endeavor with the Keck telescopes. And so after a few years working now with stars, we were looking for motions of the stars. And here you see in color red, green, and blue the positions of stars in the very center next to Sagittarius star, which is that cross, in 3 different years. And clearly you see that star, you would agree with me, moves from one year to the next. And it moves with astounding speed. If you look up there in the upper right, it moves with about 100 times the speed of the Earth around the sun. And that is incontrovertible evidence that indeed, on that distance here, there is somewhere inside a mass of a few million solar masses. So there's the same mass we had 10 years earlier, but now with a better tool, and actually also closer. We're now on a distance level of only a few light weeks. That's much smaller. But is it a black hole? Again, most people would say, not bad, but not convinced. All right, back to the drawing board. So what do we need? Well, we need a bigger telescope. Now, our Californian friends already had one, 10 meters. We pretty soon got one, an 8 meter. But that wasn't enough. We had also to ask nature to help. And nature did help us in a major way. That's rare. Nature gave us stars which are on highly elliptical orbits, as you see in this case, moving around the Sagittarius position, which is down here, on a highly elliptical orbit. And that means when they come by close, down on the left side, they were only 15 light hours away from the black hole. That's about 3 times the orbital radius of the planet Neptune, solar system scales. And when the stars there made its first turn in 2002, it moved with about 2.7% the speed of light. Unheard of. If you now make a measurement of the mass again, you come up with the same answer, but now within about 1,000 times the event horizon size. Now it gets a little bit more difficult for the doubters, because to squeeze in something which is not a black hole within 1,000 times event horizon size is not all that easy. But people did it, believe me. They did it anyhow. So it was clear that this kind of evidence is really the evidence you're looking for, but in order to basically make the case that this is a black hole in here, you also have to assume that general relativity actually holds in this kind of a regime, where it was never tested. That's another principle of physics. You have to test that your assumptions hold. But we also knew then, in 2002, that the star comes around in 16 years. So we knew 2002 plus 16 is 2018. The star would again be down there. And if we then could measure still better, maybe we could see the effects of general relativity. So we really did get to work and build a new major instrument and observe the galactic center. In the meantime, however, we had a lot of fun. Last week, I was in Prague and giving a public talk there. And afterwards, I was criticized by one in the audience that I was only playing American music. I thought this was by someone on the east of Prague. Anyhow, so these stars are wonderful probes of the gravitational potential. But in order to get still better measurements, we need all of the four 8-meter telescopes to then measure the motions of stars very close to Sagittarius star, which is here in the center, and on the scale of weeks and days, and measure them with high precision. So that's data from 21, where you can see that in the summer of 21, several stars orbited the galactic center black hole, one after the other, with very, very high speed. So it's this kind of information which we use to determine with great precision the mass, the distance to the galactic center, the potential, and can ask the question whether general relativity is truly correct in this regime. And it is, to the extent we can do this. So the first thing we are testing for is the so-called gravitational redshift. So if you have a black hole there, and a star which comes close by and sends light to us, then as the light climbs out of the potential of the black hole, it loses energy, is redshifted. And that redshift we can see in spectral lines. So if Newton is right, we would have not seen anything but a straight line here. If GR is right, you see the red curve. In the measurements, you would agree, follow the red curve and not the straight line. So that's what we would call a very clear-cut proof that the general relativity is the right theory for this effect. Another very important effect is the so-called precessions. In Newton, if you have a sun and a single planet orbiting the sun, well, that single planet will go in circles or in an elliptical orbit all the time. Not so in general relativity. In general relativity, there's a precession. Depending on the mass and the radius, that precession can be very small or can be very large. In the case of this star in the galactic center, which we've been observing, it's 12 arc minutes per 16 years. But we can see that. If we again plot here what we would see if Newton is right in a plot where we have basically so-called residual data, we have subtracted the Newtonian orbit. So if Newton is right, you wouldn't see anything. Well, if GR is right, you would expect this kind of a looping of the orbit around a Newton orbit. And what the data tell us is very clearly that we see the precessions. So click 2 down. What about, however, the region right around the black hole? We're still 1,000 times the event horizon, but we see Sagittarius star in the infrared, and sometimes it becomes very bright. And we think what we're seeing there is very hot gas, which is swirling around there, right around the event horizon. And when it does so, we can actually measure the motion. And we see that it always orbits in one direction, so-called clockwise direction. And at that distance, which is only about 5 times the event horizon size, it moves with 30% the speed of light. So if you, again, do a simple estimate of the mass, what do you get? The same few million, 4 million solar masses we had from the stars and the gas and so forth. But now, very close to the black hole. So, that is what we can do with the stars. But I told you there's another way of doing this, using photons. If there is a light source behind a black hole, and we are looking at it from the left side, then in Euclidean geometry, you would have the rays from this light source go across here. And of course, those which are geometrically blocked by the black hole would not make it to us. But the ones which go outside would, never reach us. Now, in general relativity, that's not the case. In general relativity, rays which are outside this innermost region still get bent around and therefore can be moved out of the line of sight. So what you would then expect is this: a dark central region surrounded by a bright ring. We call that a shadow. So that's just a a clear-cut manifestation of the effect of gravity on photons. And now we know something already. We know the mass, and we know the distance from our precision measurements of the stars, so we can calculate what the size of this ring should be. And it should be 50 microarc seconds. And look at 51 microarc seconds. Substantial error bar still, but pretty damn good. So that's a very fundamentally very, very sound test that indeed general relativity is right. And there is a mass on the scale of a black hole of a few million solar masses. Okay, so after 40 years, we've worked our way slowly in, ever building more sensitive and higher resolution equipment, and traced the mass, which is plotted here, versus distance. Came ever closer, there's the event horizon. And you see we've arrived pretty close to it. So is it a black hole? I leave that to you, your taste. Some physicists said yes, others would say, no, I don't still know certain quantities which you should measure. So I'm of the type who would say, no, I have to work a little harder, I'm afraid. No retirement, we've got to work harder. Okay, but that's how far we've gotten. Is there any way we can go further in a major way? The answer is yes. We would really like to go all the way to the event horizon and measure the properties of the gravitational potential there. And that will be maybe possible through a new instrument, which is a space interferometer, where you measure the distortions of space-time through laser beams. This is a mission of the European Space Agency, LISA, which hopefully in 20 years will fly. And then we can measure the in-spiral, as we say, of a stellar black hole into a massive black hole. And that's what we should hear. I don't know. So what you heard was that the gravitational waves, as the in-spiral was getting further, faster and faster, go higher and higher in frequency. And then when it makes bloop, then it fell into the black hole. And by measuring exactly these frequencies, you can then make this ultimate test we call the no-hair theorem test, which states in general relativity that a black hole is a remarkably, astoundingly simple object. It has only three properties: a mass, well, that we have measured; a spin, that we have in the galactic center, not yet measured; and the third quantity is charge. But let's forget about the charge. Everything else you don't need to worry about. There are no valleys, there are no mountains, and that's why we say no hair. Black holes have no hair. They are really the most simple objects you could think of. So that's something which maybe the younger ones amongst you would like to see or participate in. Why not? That's going to be a lot of fun. Now at the very end, let me go back and talk about the galaxies. So we now know from many observations that black holes occur almost everywhere we look. And the mass of these black holes, which you plot here on the vertical axis, again, this is a factor of 10 here, each one, and the mass of the galaxy such an object sits in is roughly correlated. Now you might say, oh, so what? If someone is heavier and bigger, has a bigger head, no? It's not that simple, because the black hole, say in the galactic center, knows in the Milky Way, because everything which comes to it as accretion comes from the Milky Way. But the stars, which you measure here, are far outside the so-called sphere of influence of the black hole, where the gravity is determined by the black hole. So the stars don't know that, that there is a black hole. So if there's a correlation, that must mean that the two were physically coupled in a physical fashion when they both were formed. And that story is one which we're currently trying to explore. When did these systems form? And we know it's early in the universe, only about a billion years after the Big Bang. How did they grow? Who was first? Who grew further? So that's many fundamental questions. We do know that as we go from our current situation and look back in time, the star formation, which is that blue curve per galaxy, increases by a factor of 20. And so does the accretion onto black holes. So they grew together, but what happened in these early times, we don't know. That's a very murky business, where in this expanding universe, the first galaxies formed by collapse in dark matter halos, and then the black holes formed as well. This is a story which will take us another 20 years to fully understand. It'll be another exciting story to learn what were the roles of these massive black holes, which we now know exist in the universe. So, the young ones, you want to go into a black hole? Okay, thank you.
Thank you very much. We have time for questions now, so you can ask the translator to translate. Reinhard also has, you have your little bug. This is for the translation.
Let me see, is the channel correct channel? Yes, I think so.
And Reinhard will answer.
Yes, yes. Mm-hmm.
Precisamente por la onda gravitacional que ejercería un cuerpo celeste, si el Sol de repente desapareciera, pero se crearía una onda gravitacional que distorsionaría el espacio-tiempo hasta llegar a la Tierra y tardaría 8 minutos en dejar de orbitar la Tierra porque es lo que tarda en llegar a la luz.
Mm-hmm. Exactly. Well, of course, I hope it won't happen, or do you?
Bueno, ¿se me escucha? Por aquí. Que debido a su experiencia en el campo y que somos muchos estudiantes de física por aquí, quería preguntarle qué consejo le daría a un estudiante de física que quiere seguir su carrera en research.
Yeah, well, thank you for the question. I do not think that I know everything. But clearly I think that the idea is do whatever makes you happy. What you're burning for, what you think is exciting, and where you have a lot of fun. Because doing research is a lot of fun. I've been playing all my life. I'm 71 years old now. I have fun. I still have fun. But it's hard work. Let's face it. It's not something you do, 30 hours a week. So do whatever you really like.
Hola. Muchas gracias por la conferencia. La verdad que muy interesante e increíble cómo lo han divulgado estos temas que son tan técnicos. Y también agradezco al Instituto de Astrofísica de Granada, de Andalucía y todos los organizadores por poder asistir. Y solo quería comentar una curiosidad en cuanto a la onda gravitacional cuando se juntan dos agujeros negros, que hemos podido escuchar la forma de onda porque está en el rango de frecuencia audible del infinito. Entonces, si en todos los posibles casos de masa y cómo son esos agujeros negros, siempre van a estar dentro de ese rango de frecuencia o hay algunas ocasiones que no están así. Y nada, muchas gracias.
Yeah. Thank you. Very, very good question. The answer is absolutely not. This is just done in order for us to be able to hear it. So, the frequencies which occur depend on the mass ratio and the mass. So if the masses are low, the frequencies are high, and towards the end they're high, obviously. But the thing is currently what gravitational wave detectors, so-called LIGO detectors, have done is to see the in-spiral of two stellar black holes. And that means that the end, which was this boop, is only about 1/10 of a second, 100 milliseconds long. So that's not very long, yet that is where all the information about the region around the event horizon is. So you would like to build up more sensitivity and signal noise ratio. So that's where the situation of a big black hole and then a stellar black hole is much better, because there it takes in the initial stages weeks before this happens, and the frequencies are indeed much lower.
Si se hubiese demostrado que en el centro aquí no había agujero negro, ¿habían otras propuestas de qué objeto hubiese habido en el centro de la galaxia? ¿O se barajaban otras propuestas, aparte de un agujero negro, de otro objeto? Muchas gracias.
Yes, of course. I mean, initially, certainly, the option would have been that indeed there is no black hole. Say there would have been a cluster of stars which make up a mass concentration, but it's not a black hole. Then we would have started to think about, well, is it the case that maybe in some objects, some galaxies, under certain circumstances you can form a black hole, like in these quasars, but in others not, because maybe in these galaxies like our own, we have developed fairly much without a disturbance, while in the quasar case, maybe two galaxies collided or something like this. So this would have been the option. That is a special case that's black holes form, but it's not what we're finding. What we're finding is essentially every galaxy has a mass concentration. Now, mind you, the proof that this must be a black hole can only be done now in the galactic center, and slowly now also in a few other galaxies. So you cannot say that you've done the equivalent hardcore proof everywhere. That we have not done yet.
Hi, good afternoon. Here.
Okay.
I want to ask something else. If from here you can measure the electric charge or the rotation of a black hole, of the center of the galaxy. It is possible from here, or you have to be
in the black hole. No, we can. There is a effect which I didn't discuss due to the spin. So if the black hole spins, then the space-time, remember the distortions of space-time due to gravity in the inner region begin to rotate with the black hole. So if then there is a star which is in this innermost region, it sees all of a sudden that the space-time is going that way, and it's beginning to wobble. So it's starting to precess about the spin of the black hole. So if we can measure this, because we find by chance, and nature helps us again, a star which is so close, then we can measure the spin from here.
Thank you very much. I really enjoyed the talk. Thank you so much. Just a curiosity. Who came up with the black hole name? Why is it called black hole?
Yeah, let's see, that was Wheeler. If you look in the literature in the 60s, then they would talk about relativistic throats. A throat, yeah, because, you know, the potential well going down. So it was Archibald Wheeler who coined that term, black holes. It must have been in the late 70s or something like this. And of course it's stuck because it's so much better. But then of course, I sometimes, as you might guess, as a joke, you get the question why black and not green.
What about the future of black holes?
What?
About the future of black holes.
Very good question. Yeah, well, okay, so basically, I hope you understood that in the early universe, the black holes and the galaxies grew together. I wouldn't say in lockstep, but approximately together. We call that co-evolution. And that was because in the early universe, the rates at which gas was transported inward to the centers of young galaxies was far higher than today. So galaxies grew fast, black holes grew fast. Now the universe is getting geriatric. And worse, it's expanding in its expansion rate remarkably, which we have not yet understood. So that means that on average, you can expect that the accretion rate onto galaxies and on black holes is going down all the time. So that means the feeding rate at which black holes become luminous active galactic nuclei will go down on average. They will stay there but not grow anymore. So it will all become very geriatric. Yes.
Allá hay dos.
Bueno, buenas tardes, muchas gracias por la conferencia. Yo tengo una pregunta. Usted ha contado un viaje de 40 años de desarrollo tecnológico para la medida de los agujeros negros, pero yo quiero saber si todas las medidas de las que usted nos ha hablado están previstas por la relatividad general de Einstein o ha habido grandes esfuerzos teóricos posteriores a Einstein para conseguir todo lo que nos ha hablado.
Very good question. The answer is many theoretical physicists consider black holes in the limit of being singularities of mass and energy, the most fundamental question of physics. It might be a little weird to put it this way. I mean, some say they're the atoms of the 21st century. Because, you know, we have in the 19th, 20th century understood atoms and nuclei and all of this. Now it's gravity, and it's astounding. I mean, we know as human beings about gravity since we exist. Yet in this extreme limit, we don't. And as I also mentioned, the problem now is how to make further progress. Because if we want to understand whether these singularities in the centers of black holes exist, you might think the best way to do this is to travel there. And I was asked on TV a week ago, if somebody promised you that you won't come to harm, will you fly into a black hole? And I said, no, because I know the promise will be broken.
Thank you very much for the talk. I have a question that I just thought about. Maybe it's crazy, but I know that the tidal forces on objects that are accreted by black holes are extremely strong. So, like the star, if the star falls into a black hole, it's not a star anymore at that point. And I was thinking whether there's very tiny, cute black hole that's falling into a supermassive black hole. Is it possible to conceive a tidal force that will rip apart the huge, tiny black holes?
No.
Black holes are indestructible.
They are indestructible in that sense. But you're absolutely right, so I should explain. If the stars which you've seen in my presentation, they're all pretty safe in the sense that they go in and go back out. Sure, they, so to speak, yeah. But that's about it. So how much closer does a star like the ones we observe have to be? Well, about at 9 times the event horizon size. So if a star like that happens to come into as close as 9 times the event horizon, then it will be disrupted. And then all hell breaks loose. Within about a half a day, the star gets destroyed, drawn into spaghetti, if you like. Half of it falls into the black hole, half of it's ejected. That happens in galactic centers like our own once every 30,000 years. We've seen it in external galaxies, actually, but not in our own. It'll take a little long time. I mean, you're younger than I am, but still, it's probably not worthwhile waiting for that event. Yeah? But black holes, no, they won't get destroyed.
Señor, buenas tardes. Gracias por su charla. Yo no soy físico, ni tan solo estudiante.
I don't have a connection anymore. So sorry. Okay. Now it's okay.
Muchas gracias por su charla. Y decía que yo no soy físico, ya no me he gustado, ni tampoco estudiante de física, pero me gusta mucho las conferencias de divulgación, y por lo que yo he leído o he visto, los agujeros negros estelares, algunos pueden venir de la explosión de una supernova, pero mi duda es, el agujero negro que ustedes han descubierto en el centro de la galaxia, ¿cómo se forma? ¿Tenemos idea de cómo se forma un agujero negro tan grande?
Thank you. Yes, so stellar black holes are almost certainly the product of the explosion of a massive star when it runs out of its nuclear fuel, and then gravity takes over, the star collapses, and then in the end, neutrinos inside have so much pressure that they push the whole thing into an explosion. And then what's left over is a stellar black hole of some fraction, 10% or whatever, of the original star. So now what about the black hole in our galaxies, or in general, the massive black holes? The standard picture has been that you start small and grow. So in the early universe, you would start as a stellar black hole, say, and then because you're in the center of a galaxy, your food menu is more rich than when you are elsewhere. So you're being fed constantly and grow. And you can then actually make simulations, or you can calculate how fast that will be at the maximum rate which you can go at. And that turns out you can double your mass every 500 million years. And that turns out to be too long for most of the big black holes we see at high redshift. So we think there must be another way to get there. And one other way of getting there is that in the early universe, not just a single star, but an entire nucleus collapsed and formed immediately a very massive black hole. The answer is we don't know. So that's what's the fun of the next 20 years. The so-called James Webb Telescope, which is up there now, is seeing objects only a few 100 million years after the Big Bang, far deeper away from us than past telescopes. And the next generation telescopes the so-called extremely large telescopes, like you are building one in Chile of 40 meters diameter, will then hopefully then go back to these objects and look at them in detail and try to understand what's happening there. And then we may have an answer. What was there? Was there a bunch of stellar black holes, or was there a single black hole early on, which would have had, as I said, basically be formed in a single bang? We don't know.
Thank you for the conference and tips.
Oops.
The black hole can actually die, or?
Yeah, okay. Those I was talking about there, no. Very small black holes probably can through so-called Hawking radiation. So this is a deep quantum phenomenon which nobody has observed yet, but that it might exist is highly plausible for anyone who understands quantum mechanics. And that is basically because the event horizon is a membrane, so to speak, which you cannot pass, right? That's what I discussed. Even light cannot pass it. But in quantum mechanics, you can tunnel, as one says. Particles can tunnel through this tunnel of the membrane. And so you can have a situation that through this quantum mechanical tunneling, a particle emerges outside of the event horizon and an antiparticle goes into the black hole. And then the black hole starts radiating and at the same time losing mass. But these beasts, no, they cannot.
A second thing, if our black hole, galaxy black hole can, if this gets active, the black hole the jets can kill us, or?
Well, okay, in principle, yes, but the reality is, as I described, the real situation in our Milky Way is that the accretion rates onto the central black hole are so low that it is, almost, this is sad to see how it doesn't produce radiation. And so it's very unlikely that there will be circumstances in the future that it spews out a lot of energy.
Hola. Me ha gustado mucho el discurso y yo quería preguntar qué pasaría si el Sol se convirtiese en un agujero negro.
What would happen if the sun becomes a black hole? Well, then as I explained, then it's an object which has a diameter of a few kilometers and it would not radiate very much. So it would be there, you can sense it, but it would not have much of a consequence. But don't worry about the sun. The sun will not end up as a black hole. That's not what we think it will. It'll become what we call a white dwarf, a very meek little weakly radiating star.
Hola, gracias. Tengo una duda. ¿Qué hay dentro de los agujeros negros?
Okay, there's a simple answer and a more contrived answer. The simple answer is I don't know. And I'm not planning to find out. The more contrived answer is, according to general relativity, inside of the event horizon, nothing can stop. Okay, if you're sitting on a rocket flying through the event horizon, and suppose you actually make it, you're not tidally disrupted, well then you cannot stop. You cannot turn around. You cannot fly out. We discussed that. So the only way you have is to fly to the center. And then in finite time, in your finite time, you end up in the center in the singularity and then you're gone. And so that happens to everything else. Rocks, cars, whatever rockets, anything you fly into a black hole will disappear in the central singularity, and that's it.
Sí, gracias.
Maybe the last two questions, please. Las últimas dos preguntas. Sí.
Según la relatividad especial de Einstein, era el espacio-tiempo el que al curvarse hace que los cuerpos sean atraídos. Pero no obstante, también se cree que los gravitones son los que interactúan los dos cuerpos celestes para que se atraigan. Entonces, ¿cómo estarían relacionados los gravitones con la propia geometría del espacio-tiempo?
Well, that's the propagation. Okay, I said in Newton's picture, if you have a mass, then the picture was that the gravitational force from that mass was instantaneously transmitted in space. In Einstein's theory, this transmission happens over time through gravitons. And the gravitons travels at the speed of light. Is that true? Yes. The measurements of LIGO have shown to some accuracy that this is actually the case. So the gravitational force, the gravitational interaction is being transported through these gravitons. But they're going at speed of light, and therefore they have no mass, okay? They have no mass.
Thank you.
La última cuestión.
Good afternoon, thank you for the conference. I was need to ask, does our own, well, you were explaining previously how some black holes can act as quasars and emit such radiation. Does our own black hole do that? Does our black hole act as a quasar?
Not if it is not fed at maximum rate. It would not even even then it would not reach the level of a quasar because the mass is not quite enough. But yes, it would be very, very bright. But for that, it would have to be fed at about almost 1 billion times, 1 billion, 10 to the 9 times faster than what it actually happens. Right now, every day or two, the equivalent mass of about an asteroid is falling in. You can see that. I mean, you can see the light eruptions in various wavelengths, but that's nothing compared to what you need to feed a quasar. Okay, thank you very much. Wonderful questions.